Welcome to The Explainer. I am so incredibly excited we're diving into this today because we are looking at something that is going to absolutely shatter your everyday understanding of scale. We're going to explore TON 618. It is undeniably one of the most awe-inspiring, massive, and frankly terrifying objects we've ever discovered in our universe. If you think you already know what a black hole is, well, prepare to have your perspective entirely shifted.
I want you to start by just asking yourself, how big can a black hole actually get? Try to imagine the absolute limits of cosmic scale. Now, we know black holes form from collapsed stars, and we know there are supermassive black holes sitting right at the centers of galaxies. Take Sagittarius A star in our own Milky Way, for example. That one is 4 million times the mass of our Sun. Sounds huge, right? But before we zoom out into the deepest, darkest reaches of space, I want you to keep that 4 million number in the back of your head, because where we are going today makes our local supermassive black hole look like a literal grain of sand.
All right, let's jump right into Section 1. Meet the ultramassive black hole, and let's scale the cosmos.
To really wrap our heads around this beast, we have to look at the sheer, unadulterated scale we're dealing with here. If you point a really powerful telescope at just the right patch of sky, right on the border between the constellations Canes Venatici and Coma Berenices, just below the handle of the Big Dipper, you can pick up this tiny bluish-white dot of light. That little speck is TON 618. Imagine our entire solar system on one side of a massive cosmic scale, and the estimated diameter of TON 618 on the other. This black hole has an estimated diameter of roughly 2,600 astronomical units. An astronomical unit is the distance between the Earth and the Sun. To put that into perspective, Neptune is about 30 astronomical units away from the Sun. That means TON 618 could swallow our entire solar system more than 40 times over, and it wouldn't even fill its boundaries.
Let's define exactly what that boundary actually is. The event horizon is the ultimate point of no return. Now, it's not a physical surface like the Earth's crust. It's a boundary where gravity becomes so incredibly intense that nothing, literally not even light itself, can escape its pull. For TON 618, this sphere of absolute darkness spans roughly 390 billion kilometers across. If you were to drop our sun right into the dead center of it, you would have to travel billions of kilometers outward just to see the light of the stars again. So the absolutely crucial point here is mass. Just how heavy is this thing? Well, one estimate puts it at 66 billion solar masses. That is 66 billion times the mass of our sun. Remember our own galaxy's supermassive black hole, the one sitting at 4 million solar masses? TON 618 is roughly 15,300 times more massive than that. In fact, if this estimate holds true, this single black hole is heavier than the combined mass of every single star in the entire Milky Way galaxy. Just let that sink in for a second. One single object outweighing hundreds of billions of stars. But, science is constantly evolving. A more recent analysis introduced a new number, 40.7 billion solar masses. And this actually introduces a really fascinating scientific debate surrounding its true size. But honestly, even at this lower estimate, the black hole is roughly 2/3 the stellar mass of our entire Milky Way. It is so unbelievably heavy that astronomers have proposed an entirely new classification just for it and others like it. They aren't just supermassive anymore. We're talking about ultramassive black holes. Moving right along to Section 2, inside a hyperluminous quasar and the physics of light.
Okay, so we've established that the black hole itself is defined by total darkness, right? It's a massive void where light just cannot escape. So how does it create so much brilliance that we can see it from all the way across the known universe? The answer is a quasar, basically an extremely luminous active galactic nucleus. Notice the really key part of this definition. The black hole itself isn't shining. The light is actually coming from the intensely hot accretion disk that's surrounding it. As the black hole's immense gravity pulls in these incredible amounts of gas, dust, and matter, all that material swirls around it at fractions of the speed of light. The friction and the gravitational forces heat this material up to unimaginable temperatures, and that causes it to glow with blinding intensity right before it finally crosses the event horizon. This creates what I like to call the illusion of light, which is just a beautiful narrative paradox. While the black hole at the center is entirely invisible, the resulting quasar surrounding it shines with an absolute magnitude of -30.7. It is so unfathomably bright that it completely outshines its entire host galaxy. We can't even see the galaxy TON 618 lives in. The light from the feeding black hole at its center simply drowns out the light of hundreds of billions of surrounding stars.
Let's look at the actual output of this engine,
Because it's staggering. TON 618 emits an unfathomable 140 trillion times the luminosity of our sun. 140 trillion! And on top of that, it sits within this colossal Lyman alpha blob. That's essentially an enormous cloud of glowing hydrogen gas that is 330,000 light-years across. That is triple the size of our entire Milky Way galaxy, and it's just glowing in ultraviolet light because it's being relentlessly bombarded by the intense radiation pouring out of this quasar's accretion disk. Which brings us to Section 3. How do we actually weigh it? Let's get into the mass discrepancy. Seriously, how on earth do astrophysicists measure the mass of an object sitting billions of light-years away? Especially when they can't even see the object itself, only the glowing gas around it? Well, this is where the detective work of astronomy becomes truly fascinating. They use a technique called virial mass measurement. Instead of weighing the black hole directly, scientists measure the velocity, the speed of the glowing gas orbiting it. They do this by looking at the width of emission lines in the quasar's light spectrum. The basic physics are actually pretty straightforward. The heavier the black hole, the stronger its gravitational pull. The stronger the pull, the faster the gas in the surrounding broadline region has to whip around it just to stay in orbit. So if you can measure the speed of the gas, you can calculate the mass of the black hole holding it there.
But this is exactly where the debate I mentioned earlier comes in. The data reveals a pretty distinct discrepancy. Back in 2004, a study by Ohed Shemer and colleagues looked at the H-beta emission line. They measured the gas moving at a staggering 10,500 kilometers per second. That incredible speed is exactly what gave us the classic 66 billion solar mass estimate. However, fast forward to 2019, and a study by G and colleagues looked at a totally different spectral line, the CV line. They found the gas moving much slower, at about 2,761 kilometers per second. And that slower speed is what results in the lower estimate of 40.7 billion solar masses.
The source literature actually puts this perfectly, noting that, quote, these lines originate from distinct regions of the orbiting gas, yielding a different velocity for the material and thus a different calculated mass. We're bringing this up because it brilliantly illustrates how science works at these extreme limits. The uncertainty here isn't because somebody did the math wrong, it's because different elements glow in completely different parts of the gas cloud. Depending on which part of the glowing cloud you're looking at, you get a different speed. Ultimately, both estimates make it an absolute titan of the cosmos, but its precise weight? That remains an ongoing scientific mystery.
And now for our final part, Section 4, a glimpse into the past and the reality of cosmic time.
To truly understand TON 618, you can't just understand immense space, you have to understand immense time. The discovery of this object is a journey all on its own. It was first cataloged way back in 1957 at the Tonantzintitl Observatory down in Mexico. But back then, they misidentified it. They thought it was just a simple white dwarf star in our own galaxy. It wasn't until 1970, when a radio survey in Italy picked up strong emissions, that scientists realized, okay, this isn't a normal star. Finally, later in the 1970s, Marie-Helene Ulrich at the McDonald Observatory obtained optical spectra that confirmed its high redshift. It wasn't a tiny star nearby, it was a monstrous quasar incredibly far away.
And when I say incredibly far away, I mean a light travel time of 10.8 billion years. The light hitting our telescope lenses right now, the light that actually allows us to measure those gas velocities, left TN 618 10.8 billion years ago. Think about that for a second. By the time that light left its source, the Earth did not even exist. Our sun wasn't even born yet. The universe was only a fraction of its current age, living in an era where there was just this massive excess of gas to fuel these hyperluminous quasars. We are not looking at TN 618 as it is right now, we are looking at a literal ghost from the dawn of the cosmos.
Which brings us to a final question that I hope leaves you as staggered as it leaves me. What does TON 618 look like today? This black hole has had over 10 billion unobserved years since the light we're seeing right now left it. Did it just continue to feed and grow even larger, pushing the theoretical limits of physics even further? Did it consume all the matter around it and go completely dark, turning into a silent, invisible titan drifting in the modern universe? Honestly, we can't know. We can only look at the ancient light reaching us now and marvel at the ultimate extremes of our universe. Thank you so much for joining me for this explainer.